This video looks at the solution to question 7 and question 9 of the curve sketching tutorial. For question 7, the first part, we have to state the equation of the asymptotes for the curve with equation y equals to x minus 1 over x times x plus 1. To look at the horizontal asymptotes, we can observe that as x tends to positive or negative infinity, the denominator grows faster as it has the highest power of x as x squared, whereas the numerator has the highest power of x as x. And hence y equals to 0, or the x-axis is a horizontal asymptote. Similarly, we have two vertical asymptotes at x equals to 0 and x equals to negative 1. Both of these values will make the denominator to be equals to 0. Next, for part 2, we have to prove using an algebraic method that the equation of the curve cannot lie between two certain values. Note that these two certain values are referring to y values. Also, since we are required to use an algebraic method, we cannot find the two certain values by observing the graph of the equation on the GC. In order to solve this problem, first, we will manipulate the equation such that we will obtain an equation in terms of x squared, a quadratic equation in terms of x, with y we will see as a coefficient of this equation. To find the values of y where the graph cannot lie, we will have to make sure that this quadratic equation has no real roots. In other words, we need to look at the discriminant to be less than 0. The discriminant with b squared minus 4ac will be in terms of y, and letting this to be less than 0, solving this quadratic inequality will lead us to the two values whereby the graph cannot lie, which are 3 minus 2 root 2 as well as 3 plus 2 root 2. Next, we are required to draw a sketch of C making clear the main relevant features. First of all, we can make sure of the x-intercept by substituting y equals to 0, which should give us x equals to 1. Also, the stationary points can be found to be y equals to 3 minus 2 root 2 at x equals to 1 plus root 2, and y equals to 3 plus 2 root 2 at x equals to 1 minus root 2. With the equations of the asymptotes found earlier in part 1, we can draw out the sketch of the curve as shown on the screen. Please make sure that you have labeled all the asymptotes, including the x-axis labeled as y equals to 0, as well as all the relevant stationary points and axial intercepts. The last part of this question requires us to show that the equation x minus 1 over x times x plus 1 minus 3 equals to negative k cosine x minus 1 minus root 2 has no real solution if k lies between 0 and 2 root 2. To solve this part, the hint is for us to consider another curve with equation y equals to negative k cosine x minus 1 minus root 2 where k is a non-negative constant. First of all, the equation that we are to show that there is no real solution is equivalent to the equation x minus 1 over x times x plus 1 equals to 3 minus k cosine x minus 1 minus root 2. Considering the graph of y equals to 3 minus k cosine x minus 1 minus root 2, we will first realize that cosine x minus 1 minus root 2 will always lie between negative 1 and 1. This is true of the cosine function, whereby the range is always between negative 1 to 1. And hence, k cosine x minus 1 minus root 2 will lie between negative k and k. And moving on, 3 minus k cosine x minus 1 minus root 2 will lie between 3 minus k and 3 plus k. And the graph of the equation y equals to 3 minus k cosine x minus 1 minus root 2 will look like this. Next, we can observe that when x equals to 1 plus root 2, we have 3 minus k cosine x minus 1 minus root 2 to be equals to 3 minus k, which is the least value of the curve. That is because when x equals to 1 plus root 2, we get cosine 0, which is equals to 1. Similarly, we can observe that at x equals to 1 plus root 2 is the maximum turning point of the graph that we have drawn in the previous parts, as shown in this diagram. So considering this graph that we have drawn earlier on, as well as the graph of 3 minus k cosine x minus 1 minus root 2, we can realize that we need k to be less than 2 root 2 in order for the graph of y equals 3 minus k cosine x minus 1 minus root 2 to fit into this shaded region between 3 minus 2 root 2 and 3 plus 2 root 2 such that the two graphs do not intersect at all. This is how the two graphs will look like if k takes on the value that's between 0 and 2 root 2. Hence, we have shown that there will be no real solution to the equation if k is between 0 and 2 root 2, since the two graphs that we have considered do not intersect if k takes on these values. Moving on to question 9. We have a curve with equation with unknown coefficients a, b, c, and d, which are constants. And we have the lines x equals to 1, x equals to negative 1, and y equals to 0 are asymptotes. Last of all, we have that c has a turning point at negative 3.5. We need to find the values of a, b, c, and d. First of all, focusing on the two vertical asymptotes x equals to 1 and x equals to negative 1. Since they are vertical asymptotes, it means that x squared plus d must be equals to x minus 1 times x plus 1 because these are the two values that give the denominator of the equation to be 0. Solving this, we get d equals to negative 1. Next, if y equals to 0 is a horizontal asymptote, it will imply that a equals to 0. That is because if we perform a long division on the equation, we will get a plus something else over x squared plus d. And since y equals to 0 is the horizontal asymptote, a in this case has to be 0. At this point, we are left with points c and d to be found. Now, our equation with the values of a and d found is equals to bx plus c over x squared minus 1. Performing a differentiation, we can get dy dx, and since at negative 3 negative half, it is a turning point, that means dy dx equals to 0 at x equals to negative 3. This will give us one equation whereby negative 5b plus 3c equals to 0. Next, since negative 3 negative half is a turning point, it lies on c as well. Substituting x equals to negative 3 and y equals to negative half will give us a second equation whereby negative 3b plus c equals to negative 4. Solving 1 and 2 simultaneously will give us b equals to 3 and c equals to 5. Next, we need to find the coordinates of the other turning points. Looking back at dy dx and putting all the values of a, b, c, and d, solving for dy dx equals to 0, we will get two values of x, which is equal to negative 1/3 or negative 3. Since negative 3 is the given turning points, the other turning points will be at x equals to negative 1/3, and the corresponding y value can be found to be negative 9 over 2. Last of all, we have to sketch C. This is how your graph should look like. Take note to label all the asymptotes as well as the x and y intercepts.